Presented by Caltech.
Why don't we start? I would like to welcome you to today's CaJAGWR seminar. It is my pleasure to introduce our speaker today. Is Carver Mead, Gordon and Betty Moore, Professor Emeritus of Engineering and Applied Science here at Caltech. Carver is one of the pioneers of modern microelectronics, and his work underlies most of the technology we enjoy today, including your cell phones and computers. Carver founded Caltech's own computer science division. He worked with Feynman and Hopfield in neural networks and the physics of computation. For all his work, this is just a little bit, it's impossible to list here his almost infinite accomplishments, but because of all of that, he was awarded in 2002 the National Medal of Technology. Carver also is known for coining the phrase Moore's Law, which is very funny. But he's not going to talk about any of that today. He's going to tell you about his ideas about gravity. So why don't you join me in welcoming Carver. Thank you.
Thanks, Max. Well, it's good to be here in the CaJAGWR seminar. I always thought that was such a great name for a group. And a group with that good a name, it seems to me, should have a logo. So I think you should have a competition for the best logo for the CaJAGWR group. And since I'm giving a talk today, I thought maybe I could put in a couple of early entries. So, how many here think the one on the left is the best logo? Maybe 3, 4. Okay, how many think the one on the right is the best logo? Okay, well, the one on the right has got it so far. And then from now on, you're on your own with the rest of the competition. When we were in grade school or high school, we all learned about the two great forces, the long-range forces, gravitation and E&M. And everyone since has been struck by the fact that they're of the same form, but of opposite signs. And what could that possibly mean? And could they be related? And that's been a recurring theme down through hundreds of years. And then you have force laws, but what good are force laws? So there's a force. So what good does that do you? Well, we're told that Newton said that a force is a thing that changes the momentum. Okay, I guess. So we have the two great forces from charges attracting each other and massive bodies attracting each other. And those forces are supposed to change the momentum of bodies. And we've had this beat into us since we were young enough that we can't remember where it came from or what it means. We just have it deeply embedded in our psyches. So here we are. Here's a thing with momentum. And at some point, a little guy there pushes on it and applies a force for a long time. And the little vehicle gradually gets faster and faster and faster, and finally the guy lets go of it, doesn't push anymore, and the velocity keeps it just going. Well, that wasn't Newton, that was Galileo who figured that one out. So already we can see there's a little funny thing going on. But that's a very old idea, and this is all grade school stuff. So is there anything more modern that might have something to say about this? Well, here's a thing with inertia, and it doesn't look at all like that little car. It's a superconducting magnet. It's one that I use in a lab. It's about 2 inches across here and about 3 inches long. And it has 2 wires. And between the 2 wires, all wrapped up in that cylinder, is about 1 kilometer of superconducting wire. And the wire has about 10 to the 20th electrons per meter in it. So it's a pretty simple thing. And if you do the experiment on it, you come along and you apply a voltage to those 2 terminals, and you leave it there, and you notice that the current, which of course is the movement of the electrons, goes up, and it goes up in a nice steady way, just like this was a thing with inertia. And then if you take the voltage away by, for example, put a superconducting short across the 2 wires, then the current just keeps flowing. And as far as we know, if you do it well, it'll keep going. The limits on it are very low and still haven't reached where we can actually measure. So this is a wonderful inertial system. And it's nice to think about in the context of electrons instead of some vehicle with wheels and that sort of thing. So let's just do a little engineering calculation here, since this is an engineering approach. Let's see, how much force are we applying to each electron? Well, the force per electron is a charge on the electron times the electric field. The charge on the electron we know, that's this thing over here. The field is just the voltage divided by the length. We put a 1/2 volt on it, so it's 1/2 volt over the length, which is 1 kilometer. So this turns out to be 10 to the minus 22 newtons on every electron. Okay? That's a nice small number. Well, how about the current? Well, the current is the charge on the electron times how many there are per meter, times how fast they're going in meters per second. That's now charge per second, which is amperes. And if you put numbers in, it turns out to be 16 times the velocity in meters per second gives you the current in amperes. So here we are. We started down here, and we waited for 40 seconds to get these 40 amperes of current. And at 40 amperes is 2.5 times the 16 there. So now we go down here to something Newton gave us. The inertial mass of this system will be the force here divided by dV dt over here. And when you put that in, you get 1.6 times 10 to the minus 21 kilograms. And you say, oh yeah, electrons are light little things. They are light little things. A free electron has a mass of 10 to the minus 30 kilograms. So then, of course, you go back, you say, oh, I left something out. No, you didn't leave anything out. The inertia of those electrons is 10 to the 9 times the inertia of an electron out by itself. Well, that's cause for pause. I should remark in passing that our whole electrical technology depends on the fact that the electrons in electrical machinery have vastly more inertia than they do if they're just little things out by themselves. We wouldn't have any of our electrical technology today if that were not true. Well, let's look a little closer at what's going on in there, because it'll help us. There's, as we said, a kilometer of wire with 10 to the 20th electrons, but the part that nobody knew back in the old days was that when the electrons go into a superconducting state, they make just one big quantum wave function. And as long as you don't mess with them too badly, it behaves just like a system with 1 degree of freedom. It's like saying I can represent a mass by the properties of its center of mass. Well, the wave function has some envelope. That envelope is just the thing that keeps them in the wire. And then it's just a propagating wave. It has a propagation vector, and it has a frequency. Frequency related to its energy, which in this case, is related to the voltage on the particular point in the wire, and the propagation vector related to its inertia. Well, we're used to electrons being wave. This is a particularly nice diffraction pattern that was made by taking a nice collimated beam of electrons and putting it through a very thin crystal. And we're reminded that this whole thing started with Max Planck, who said that somehow the energy was related to the frequency and gave it a constant. And then de Broglie came along 13 or 14 years later and said, well, if that's true, the momentum must be related to the propagation vector. And then shortly after that, Schrödinger came through and said, no, you left something out. The momentum is really, and by momentum here he means the mass times the velocity, is equal to what you said, de Broglie, minus the charge times the vector potential. So in addition to having the scalar potential that causes these things to attract each other, you have this vector potential which interacts only with things moving with respect to each other. Well, that's interesting. So let's look at what's going on in the superconducting solenoid. It has a current here, and that current is just the charge of the electron times how many there are per unit length times the velocity. This is what we did before. What we didn't do is to see what the wave function's doing. It has the propagation vector minus the vector potential. Well, what's the vector potential? Well, the vector potential is proportional to the current, which is proportional to the velocity. And it's this big integral. The current here, where it's sensing the vector potential is just adding up all the little currents everywhere, dividing by the distance they are away, and making a single resultant vector out of that. That's all it is. So this term here, the QA part, is proportional to the velocity. And it's minus, which means the harder you push on the thing, the more it fights back. So there's a built-in feedback loop. Whenever you have these coupled systems, there's a built-in feedback loop that makes the thing that's interacting have a very different inertia than it would have had if it wasn't interacting with other things. So that's the big lesson that we can take away from E&M, is that you couple a bunch of these things and it really affects the inertia a lot. Can be huge. In this case, it was a factor of 10 to the 9 more in the coupled system that would have been in the individual electrons. Well, that's interesting. So A lot of people thought about this. This is Einstein in 1912. You can see right here on the picture. I hunted hard to find this picture. And you notice he's a very sober, very pensive Einstein. Now, why is he so sober and so pensive? Well, you know, he had a great year in 1905. He did special relativity and Brownian motion and, you know, things that people remember. And right after that, he started working on gravitation. And the first paper he published on that subject was in 1907. And he struggled with that for 4 more years, and then he wrote his next paper, which is actually my favorite of all of Einstein's papers. And it was on the influence of gravitation on the propagation of light. It was based strictly on the equivalence principle. And just using that, he reasoned his way to the fact that the speed of light must depend on the gravitational potential. It's a wonderful paper, and we've gotten a retranslation done in the last few years that's clearer than the original. If anybody's interested, I can give you the reference to that. It's on the web. In this paper, he made 2 absolutely remarkable predictions. He predicted there would be a gravitational redshift, that clocks of any kind would run slower when they're near a massive body. And he predicted that light would be deflected as it went around a massive body. It turns out we consider these today 2 of the great triumphs of general relativity. This was 5 years earlier than that. So let's see how it works with Einstein's theory, his early theory. He said that the velocity of light is the velocity out in our part of the universe, but not near any local massive bodies. So it's sort of the average of the interaction with all the rest of the universe, times 1 minus gm over r c squared, r being the distance we are from this local massive body. And gm over c squared comes up so much, we're just going to call it delta for now. So it makes the... Well, what's the resonant condition for this resonator? This was Einstein's favorite clock. Just 2 mirrors and light bouncing back and forth between them. Well, it's an integral number of half wavelengths in the length. Well, k times the length is the total phase, so that has to be n times the pi wavelengths. And k is equal to omega over c. That's just because light is non-dispersive. So that says that the frequency is going to have this standard constant out in front, which you think was constant. And it's lessened by this delta factor. So in this theory that he put forth, the lengths did not change with gravitational potential. Gravitational potential is representative, or represented by the speed of light. And if you work it out this way, it turns out that this works for atomic clocks and it works for nuclear energies and all those things. This was not observed until 1960. Nowadays, clocks made with resonators like this are good to a part in 10 to the 16. And a couple of years ago was demonstrated that if you took one of these clocks and synchronized it with another one and then jacked it up 1 meter, you could easily distinguish the frequency difference. So we're getting to where we can see effects that we could only dream about in Einstein's age. This was one of the dreams he had that turned out to be right on. Well, he also talked about the deflection of light. You can see how that works. This is just another little engineering calculation. It's not as complicated as it looks. We say the light's going to propagate from this point over this path down to the other point along this path. And it's going to go some distance d from the massive body. And our job is to figure out what d is. Now, we know that the curve isn't exactly this, but it's not far off. The difference between this and the actual curve, due to a little curvature in there, is going to be second order effect. So let's just find out. If you take it too far out, if you make d too big, then the light has too far to go. If you make d too small, it's getting close to the massive body and the speed of light's getting really slow. So it takes too long. So there's going to be a place in the middle where it's just right. It'll take the minimum time to get there, and that's the one we're looking for. Well, here's k. It's the one we just wrote down. Omega over c0 times 1 minus this delta term. Well, we can integrate that. The phase is just the integral along the path of the propagation vector d distance. Propagation vector is 1 over length. The distance is length. So this is a unitless thing, like a phase should be. And you get what you'd expect. You get an r term and an r2 term. That's just the length if it went straight. But then it's a little further because it has to go up and around, so the d term comes in, and it comes in second order, just like you'd expect. And then there's the part over here, well, due to the slowing of c with the scalar potential. And well, okay, now you take the derivative of the phase with respect to d squared, it's just because d comes in second order, and you get this expression. Well, Einstein considered the case where the distance to the star was very long compared to the distance from the sun to the earth, because he was looking at the deflection of light that went around the sun. And so he said, well, this 1 over r1 term can be neglected, so this is equal to that. So d has to be 2r2 delta. And now the angle is just d over r2, so that's just this delta term over the distance. Well, you've all heard the middle part of this story about how this got the deflection of light wrong, and therefore Einstein had to go and find a better theory. Well, that's true, but not exactly in the way you've been told. So let me tell you what really happened. Einstein, in this paper in 1911, wrote this paragraph. I think it is one of the most amazing predictions ever written by a human being. Said, light's going to go past the sun and be deflected by almost an arc second. It's going to appear, if it goes around a massive body, to be further out than it really is. That's what happens, of course, if the light bends this way. And then he made a plea to the astronomers. Please try to see this, because when we have a total eclipse, stars near the sun are visible. And independent of how much you think this is a crazy theory, this is an interesting question. That's Einstein. Well, as you know, between that and the time there was a good eclipse to look for this, Einstein had gone off and done general relativity, found out that GR predicts a factor of 2 larger, and Eddington got funding for a expedition. It was quite an ambitious thing. They sent a party to northern Brazil and a party to an island just off the west coast of Africa. And they had enormous practical problems to get anything at all. They got a few plates which were of quality enough to actually make this comparison, and here's the data. This is the prediction of his published 1911 paper. This is the prediction of GR, and the points are the data. Well, everybody looked at that and said, that proves that GR is right, and off they went and never turned back. But there's a postscript to this story that never gets told. Einstein wrote just a year later, wrote a very short paper in the most obscure journal you could imagine, a journal of sanitization and health something or other. And saying, is there a gravitational effect analogous to electromagnetic induction? This is my second most favorite paper. Probably should be the first, but it relies heavily on the other one. And in this paper, he made 3 more absolutely amazing predictions. He made the prediction that if a test mass was near a very massive body, its inertia would increase. That if the little test mass was inside a spherical massive body with a massive shell, and you move the massive shell, the test mass would move with it, albeit very slowly. But it would have induced in it a fraction of the motion of the large massive shell. The reason it was a shell, of course, was you had to get rid of the scalar interaction, or otherwise it would go roaring off towards any mass in sight. And then the last thing, which is the one I like the best, is it provides you a way to imagine that all of the inertia of matter is due to its movement relative to all the stuff in the universe, which is an idea that Mach put forward and Einstein fell in love with. So here's the picture out of that 1912 paper. And he makes these predictions just the way you'd expect, flat out. The way he got rid of the scalar effect, of course, was using this result from static electricity, that if you're inside an equipotential thing, then the 1 over r squared dependence makes it independent of where you are. So let's see how it works with light if you include this vector interaction as well as the slowing of c with a lower gravitational potential. Well, here we are. K is just omega over c, but it also has this 1 minus gm over c squared due to the vector coupling. Remember, K got bigger. So it's omega over c times this factor due to the vector coupling. Well, c is already smaller due to the scalar effect on the speed of light. So k ends up being this thing, which is just omega over c, where it was out where there was no massive body, and then 1 minus this little delta term. So the vector and the scalar effects add. And because the thing's going at the speed of light, they're equal in magnitude. So the total effect is double. So Einstein only had to write this one slide, and he would have had it in 1912. That's how close he was. So his predicted deflection is exactly what's observed. And I don't have to remind you that this is arrived at in a very different way than the standard treatment you see. So there's another aspect to this. The top part's just what you've seen already. But you notice that the little delta term has doubled because there's the part from the scalar and the part from the vector effect. And remember when we computed it before, we got this log term in the delay. Well, if you work it out a little more carefully, you get this logarithm. In addition to just the distance divided by the speed of light out there, you get this log term. And you say, well, log terms are always smooth and they don't do very much. Well, be careful. If d is small, this square root gets arbitrarily close to the distance here. So this could get very, very small. So this log can get pretty big. And we now call this the Shapiro delay, after Erwin Shapiro, who predicted it in 1964. He predicted it from general relativity. And he had a heck of a fight on his hands to convince people that the light could slow down because, after all, I'm sitting in my platform is in free fall, and I'm transmitting a signal to another planet and looking at the reflection. How could that possibly slow down? Well, now everybody has worked it out with GR, of course. Erwin's a quite remarkable fellow. He figured this out in 1964, and then he went and reworked the Haystack Observatory, completely put a new, much higher power transmitter and a much more sensitive receiver. And in the last part of 1966, he got his first bounces off of, I think that one was Mercury. I don't have the data from that one. It wasn't very good. But by the time he got to early part of 67, he was getting pretty good data. Remember, this would all be totally flat. It's the combination of the vector coupling and the scalar coupling that give you the magnitude you actually see. So because it's light, the vector coupling is a much bigger fraction of its inertia than if it were matter, which has a built-in mass. By 1970, Erwin had things working much better, and you can see this wonderful, wonderful example of the Shapiro delay. This time it was with Venus, and they got a nice close superior conjunction, so I was able to. Nowadays, this is a binary pulsar that was relatively recently found and identified, and it has the great advantage that we're looking at it almost edge on. So when the pulsar is orbiting the white dwarf here, the beam to Earth comes very, very close to the companion, and you get this wonderful, wonderful big peak, which exactly fits that expression that I showed you. It's wonderful. that expression was another thing he could have had in 1912 with the factor of 2. So what we've really been saying is that the electricity and magnetism taught us that there's a scalar potential, which is how charges interact with other charges. And there's a vector potential, which is how moving charges interact with other moving charges. Well, what's different? Well, the scalar potential for gravitation has the opposite sign. So like things attract instead of repelling. And the same is true for the vector potential, which means if you started out with a little element of matter that wasn't propagating, and you move the shell around it, the matter would move with it because the difference has to be 0. Well, the frame of reference issue that was brought right to the fore and predicted by the 1912 paper wasn't really found experimentally in its pure form until, well, the experiment was started. Gravity Probe B was launched 10 years ago. And we didn't have the final report until 3 years ago, or 4. What it was a little free-floating test mass. In this case, it was spinning. And it was in orbit around the Earth. Now, they always draw it this way. And I think that's a bias that's put on by GR. Because this little ball is in free fall. Its coordinate system is absolutely as good as anybody else's coordinate system. So from its point of view, which is the only point of view you care about because that's what you're measuring, the Earth's going around it in a big circle. So it's just like Einstein's shell. If you move the shell, the mass moves. If you rotate the shell, the mass would move inside. It's a very small effect because this mass is much less than the rest of the mass in the universe. But it's also a little more complicated because this is the magnitude just straight out Einstein's 1912 proposal. For this one, because the little test mass is spinning, there's a spin-orbit coupling, it just turns out to be half as big and of the same sign. So you get 3/2 of this value. And the total is called a geodesic effect, even though the two effects that you add together are quite different. This one would go away if the little gyroscope were not spinning, but the other one would still be there. So this experiment would have seen 2/3 the effect if the thing had not been spinning. Problem is that the spin of the gyroscope was what gave the London moment, which allowed the position to be determined very precisely. So couldn't do the experiment that way. This was a marvelous test, a pure test of the vector coupling. And we didn't have it till recently. I think Einstein would have been very pleased by this. Well, once you know for a fact that there is a vector coupling, and you know its magnitude, and you believe that the vector and scalar effects are related as a 4 vector in a region where there's not a big gravitational field, you realize that the ratio of these two effects is c squared. And the fact that when Gravity Probe B results were published, they were published as agreeing with GR, really means that this was the C that we know and love. So that means, in my book, there must be propagating solutions at velocity c. And that's the first time that I personally believed it. I wasn't at all sure that that's what we'd find. I'm delighted that's what we found. So that brings us to why we're here. The vector potential is a propagating solution. It depends on the momentum at some time earlier than we're looking for it, and it's a 1 over r potential, and it has this g over c squared in it. So it looks, from the propagating wave perspective, it looks exactly like an EM wave. The sign doesn't change anything because half the time the mass is moving one way and the other half of the time it's moving the other way. So all that is a phase change. So you can think of this as just a different form of electromagnetic wave. Already at this point, by just writing down this Green's function, we have made a prediction that's different from GR. When I first started getting into this, I was very concerned that what I was coming up with was just a sort of a poor man's rendition of GR. So of course I had lunch with Kip Thorne right away and said, hey, tell me if this is all well known. No, I said, this is interesting. So that's when I started talking to Max and Alan and getting serious about gravitational waves. And you can see here, because this is just a Green's function, it's just the momentum vector retarded by this time. Well, for a binary system, one momentum's always the equal and opposite of the other one, because they got nothing around to put the other momentum to. So that tells you immediately that if you stay on the line perpendicular to the orbits, where the distance between the two is equal, the vector potential you will get is 0. We can work it out. I worked it out here for a circular orbit. It's just a little simpler. You can do the eccentric orbits. They're just more complicated. But this is looking down on the orbit. Here's the two masses, equal and opposite momenta. And then you're going to look at it at some inclination angle, I here, or iota. And so we're way out there someplace. And if we're out in the y direction, you can see here that according to G4v, there'll be no radiation whatsoever. According to GR, there'll be a maximum in the radiation. So now we know for sure that it isn't just the same theory warmed over. This is a strong prediction. There's also a slight difference in the total radiation from a binary system, a Kepler system, that has eccentricity. That epsilon here is the eccentricity. And it turns out the calculations couldn't be more different. But when you write them down, this one was first written down by Landau and Lifshitz, and later worked on pretty heavily by Peterson Matthews here at Caltech. And so this is taking a Kepler orbit that you would get just from Newtonian gravity, and then using that to calculate the gravitational radiation. And when you do that, all this stuff is the same. And then there's this eccentricity dependence, which is very slightly different for G4v than it is for GR. And so, of course, I wanted to look into this because it would be really neat if we had a good test case. Well, unfortunately, almost all the test cases we have are very low eccentricity. The pulsars are, of course, the place you look for this because they're stable enough to really see something. We have one good high eccentricity pulsar, and that was the first one found in a binary, so we were lucky. And here's the integrated time difference over the 10 years or so since we've been observing it. And you see it looks like it fits within very small factor of GR. In fact, it even says here GR prediction. So of course I had to go look that up and figure out what was going on. And it turned out that if you look at the data actually coming in, referred to the Solar System Barycenter, it matches G4v better than it matches GR. But it has to be corrected because it's thought that the part of the galaxy where this object is located is accelerating relative to the Solar System Barycenter. I have no expertise in deciding if that's true or not, but it's a pretty big correction, 1.5% or so. And that makes it match with GR better than with G4v. I do know one thing, and that is both of these expressions come from pure Newtonian Kepler orbits, and those are just not right. I've worked out pretty good approximation to the corrected orbit in G4v, and there are corrections that look like they might be of this order, but I haven't gotten good enough to get down there yet. So that's work to be done. In any case, I would say the jury's out on this one. I would really love to get a high eccentricity system that's close enough to Earth that we can do a long baseline interferometry on it and find out if it's accelerating, find out really where things are. We don't have one of those yet, but the astronomers are busy. And now there's another way, which you would expect from now, that G4v is different from GR, and that is in the detector. Remember that the vector potential here is just if you had a little free-floating mass point and you applied a vector potential by like moving that shell of Einstein's, the vector potential is just the speed that would be induced in this little free-floating matter. Well, that sounds a lot like a gravitational wave detector. So let's look at what it looks like. These are free-floating objects, massive objects, not very massive objects. Here's a gravitational wave coming along here, propagating in the direction r. And here's the vector potential. It's down here, up here, down here, and so forth. So as this wave comes by these two little masses, they pick up a velocity due to the vector potential, and they're both moving down the same velocity. So the distance between them doesn't move. Okay, that was a strikeout. Well, let's put them along the direction of propagation. Okay, now they move in opposite directions, one down, the other's up. But remember, these are very small motions we're looking for. You all know just how small motions they are that we're looking for. And so this will be a second order change in the distance between them, not the way to make a detector. When I originally started working on this problem, I thought that I had a way of showing that it wasn't going to work. But one last attempt, I actually worked out what the dependence was, and of course, it's the product of the dot of the cavity onto the vector potential with the dot of the cavity onto the direction of propagation. So if either one is 0, you get 0. But if they're at 45 degrees, you get a very nice response. This one goes down and that one goes up, and they move apart very nicely. So you see that all the antenna patterns have this very nice maxima out at 45 degrees. In case of the other polarization, the maximum is out 45 degrees in the vertical direction. And once again, there's 0 perpendicular to the plane of the detector. And for GR, there's a maximum there. So Max here and Alan have worked out a very nice way of actually seeing if this is going to be detectable. As you know, we have 2 of our very own LIGOs, one up here at Hanford, Washington, underneath that cloud, and one down here in Livingston, Louisiana, underneath that cloud. And of course, as the Earth spins around, those antenna patterns are scanning the sky. So if you had a pure wave coming in, there's this one polarization, you'd see this dependence with time of day. And you notice it has sign changes. And that's in the kind of coherent detection we do, you can see the sign changes quite well. So, well, it's still, you look at it and you say, well, it looks like it might be different, but this thing looks a whole lot like the upside down of that thing. And well, Max went and worked out for the Crab pulsar, which is a highly likely thing to be giving us gravitational waves. And he said, okay, if I put in a synthesized GR wave and look at it with a GR matched filter, of course I'll get more output from the filter when I put a louder wave in. If I look at it with a G4v filter, you have to be awfully loud to see anything at all. So they're highly distinguishable. And vice versa. This is if I look for a G4v wave with a G4v filter, and if I look for a G4v wave with a GR filter. Well, until this work was done, people were looking with this green filter. So if we'd have had a really loud G4v wave, we wouldn't have seen it. There's a whole new LIGO coming up now, and we all hope we see a lot of things. Max and Alan also worked out a very nice way that's agnostic as to the theory of gravitation, that any polarization that could possibly be present will be detected, and the penalty you pay in sensitivity is not much at all. So that was a beautiful piece of work built into the LIGO library now. Well, here's Einstein. Everybody said he had a wonder year in 1905. I personally think my personal wonder year from Einstein was a summer of 11 to summer of 12. It was an absolutely amazing thing. He predicted these post-Newtonian things, the gravitational redshift, the slowing of light with gravitational potential, deflection of light with a massive body, inertia due to an object being close to other massive bodies, and the vector influence on the frame of reference, the thing. Unfortunately, the only one that was done in time to be absorbed in any of this was the deflection of light, and in many ways it's the hardest from our present perspective, with our present radars and our present antennas that pick up pulsars. That's the hard way to figure out the speed of light out there and how it's affected by the gravitational potential. The Shapiro delay is a much, much easier way to do that. So what's G4v? Well, G4v is a continuation of Einstein's early gravitation, the 1911-1912 work, just putting in the context of electromagnetism and what we've learned about that, finding a clean way of representing it, treating massive objects with their wave functions, which of course wasn't known at all when all of this theory was put together. And the coupling here is this thing K0. That's the Compton wave number. And that's the thing that stays constant when you change the speed of light. And a representation that all particle physicists know and love. When you do the coupling this way, you don't need a force law. So there's all sorts of arguments why you can't do a theory this way because it doesn't work with the force laws we have. Well, you don't need a force law to do this. Sometimes handy, but you don't need it. So the good news is it works with all the tests of gravitational theories that have been done. It's in violent disagreement with respect to both sources and detection of gravitational wave, about as far off as you could get. And the things I like about it, in addition, are it naturally encompasses Mach's principle. That inertia comes from any interaction with other stuff. And that's true of electromagnetism, and it's true of gravitation. And that means that all of our local physics has a cosmological origin. Now, cosmology is a big subject, and this is obviously not the place to do it, but I have done a little toy cosmology, and the surprising thing is you can do a very simple cosmology with very few assumptions, and you get a consistent cosmology, namely the Mach's principle integral form of the cosmology agrees with the differential equation formulation. And when you do that, you get a value for the energy density in the universe, and it's about a factor or 2 higher than you get from the standard lambda CDM models. And it works without dark energy. In fact, it's agnostic as to what form of energy there is out there, whether it's matter or other stuff. What kind of matter doesn't matter. It's just energy. So I think Einstein's 1911, 1912 thought process are worth following. Whichever way it comes out, it's going to be decided. It's going to be decided right here with this group. The jaguar will bite. So good luck with that.
We will take a couple of questions, and then there will be refreshments outside. I'm sure Carver can stick around. Yes. Ewan.
What happens to Einstein's cosmological constant at G4v? Does it disappear, or do you still have a free variable?
The G4v is inherently an integral formulation, so there's no equivalent fudge factor to play with. It's just you add up all the stuff that's out there, take 1 over r, and that's what you have.
So it's gone.
Yeah, there's no equivalent thing. And it's a good thing because it wouldn't work if there was.
So your gravitational waves are essentially spin 1 waves, correct? You know, the ones predicted by GR are spin 2, and yours, since it's a vector kind of form, should be spin 1.
It's one vector, but people, because it's a transverse vector, people typically break it down into, like if you have a binary system, they break it down into the vector in the direction the thing is rotating and the vector along the inclination direction. It's just habit. It's just what people do. So I broke it down into those two things, but really at any one place it's just a vector varying with time.
So it should be a spin 1.
Yeah.
But then in that case, you know, there are formulations of GR which are not, which are geometric. So there are spin 2, spin 1, and spin 0 waves in general for metric theories of gravity. And so yours should fall into one that is characterized by waves in spin 1. So there is a standard literature where you can find the response of the interferometer, the antenna patterns, and so on and so forth to that.
There's lots of lore for waves like this. There's a lot known.
Yeah, I think the calculation you were showing in terms of the antenna patterns on are already in the literature, if indeed your theory falls into that.
Yeah. It's no different than the antenna pattern you get with standard Maxwell's equations.
Yeah.
It's just a lot easier to get when you use a Green's function than it is if you have to go through all the matching boundary conditions and all that stuff. So as a matter of fact, I spent 10 years of my life doing E&M over again. Just because it's so much easier to do. And that's, for any of you interested in this, it's in this little green book. And that was what got me started doing E&M over, because I was interested in this line of thought that Einstein had gone down. And I realized that no way with Maxwell's equations is there anything going to be obvious. And it better be pretty obvious if you're going to believe it. So that's why I went down the vector potential path. And it's amazing to me how much easier it is, especially for antenna problems.
One last question? Yeah.
There's something known as gravito-electromagnetism. Machoun is one also who does it, which is usually presented as a linearized approximation to GR.
Yeah.
You said it comes to the same equations you have, so that G4v is like saying GM is the correct, gravito-electromagnetism is the correct theory of gravitation?
I don't know enough GR to answer that question 100%. I've seen it applied to the radiation field of gravitational radiation. And as you could see, this kind of a theory gets a different polarization than
I don't think usually GM, they don't try to do that. They use it for things like G4v.
Yeah.
Effects on point masses and on
Yeah.
field currents.
So I've never understood how far it goes and what it's really good for. And I do know that they start with Maxwell's equations like things, and of course that makes it 10 times more complicated than it has to be. And also leaves you with some some dangling constants like you pointed out.
So let's thank Carver again.